Hello everyone, welcome to the session 4 of module 3. In the previous session, we concentrated on perceptron, representation power of perceptrons, the perceptron training rule. In this session, we shall discuss on gradient descent and delta rule, visualizing the hypothesis space, derivation of the gradient descent rule. As we discussed in the previous session on perceptron training rule, that learning procedure can be proven to converge within a finite number of applications of the perceptron training rule to a weight vector that classifies correctly all the training examples, provided the condition is the training examples are linearly separable and provided a sufficient small learning rate is used. In this topic, that is gradient descent and delta rule, the perceptron rules finds a successful weight vector when the training examples are linearly separable, but it fails to converge if the instances are not linearly separable. So we have the second training rule, which is called as delta rule, which is mainly designed to overcome these difficulties, which means that if the training examples are not linearly separable, the delta rule converges towards a best fit approximation to the target concept. So the major key idea behind the delta rule is to use gradient descent to search a hypothesis space of possible weight vector so that it will be used to find the weights that best fit the training example. And moreover, this rule is very important because this gradient descent that provides a basis for our next upcoming topic, that is backpropagation algorithm, which can learn networks with many interconnected units. And also this is very important because gradient descent can serve as the basis for learning algorithms that must search the entire hypothesis space containing many different types of continuously parameterized hypotheses. Here you can see the delta training rule to best understood by the considering the task of training an unthreshold perceptron, that is a linear unit for which the output O is given by a vector of weight multiplied with vector of instances. So the linear unit corresponds to the first stage of the perceptron without the third threshold levels. In order to derive the weight learning rule for linear units, let's begin by specifying a measures for the training error of hypothesis, that is weight vector, which is related to the training examples. So there are so many ways to define this error. One common measure that we use for our convenience is given as E of W is equals to 1 divided by 2 TD minus OD to the whole square. So here where D is the set of training examples, TD is the target output for training examples D, and OD is the output of the linear unit for the training example D, and the last term is E of W, that is vector of weights, which is simply of the squared difference between the target output and the linear unit output summed over all training examples. Here we characterize E as a function of vector weight because the linear unit outputs O that depends upon these weight vector. The next is we shall see on visualizing the hypothesis space. So to understand the gradient descent algorithm, it is helpful to visualize that entire hypothesis space of possible weight vector and their associated error value. That will be illustrated in the next figure. So in this diagram, the axis W0 and W1 that represent the possible values for the two weights of simple linear units. This W0, W1 plane that will represent the entire hypothesis space. This vertical axis that indicates the error E, which is related to some fixed set of training examples. The error surface, which is shown here, that will summarize the desirability of every weight vector in the hypothesis space. This arrow shows the negated gradient at one particular point, indicating the direction in the W0 and W1 plane, which producing steepest descent along the error surface. This gradient descent search determines a weight vector that minimizes E by starting with an arbitrary initial weight vector, then repeatedly modifying it in a small step. See, at each step, this weight vector is modified in the direction that produces the steepest descent along the error surface, which is shown in this figure. So this process will continue until you get a global minimum error is reached. See here in this diagram, you can see that is a plane W0 and W1 that will represent that entire hypothesis space. Here you can see the maximum error value, and also you may have multiple minimal error values, which is drawn over the error surface for a linear units W0 and W1. See, in this diagram you can see some of the local minimal values. You may have multiple local minimal values, and finally you have only one minimum value compared to all other local minimals. That is called as a global minimal value. See, given the way in which we choose to define E for a linear units, this entire error surface must be a parabolic with a single global minimal value, which is shown here. This specific parabolic will depends on a particular set of training examples. Here you can see one set of a parabolic like a structure here, where you have a maximum error value, and this is a minimum error value. So here this gradient descent search that will determine the weights that minimizes this error value from this point to this point. So how does it works? Initially the weight vectors are taken randomly, then modified step by step, that is altering your weight values at each step. So that weight vector which may produce the steepest descent along the error surface. So this will continue until you find a global minimal error. I hope you have understood this hypothesis space. This hypothesis space may consist of many local minimal values and one global minimum value. See, in the previous diagram we have seen some of the local minimum value and one global minimum value. So to identify the global minimum value, we need to calculate the direction of the steepest along the error surface. So how do we calculate that? Let's see that one. See, the direction of steepest can be found by computing the derivative of E with respect to each component of the vector value, that is weight vector, and this vector derivative is called as the gradient of E with respect to E, which is shown here in this equation. And this entire term is itself a vector whose components are the partial derivatives of E with respect to each of the weight. Here you can see the weights are W0, W1, W till Wn. See, when interpreted as a vector in the weight space, the gradient specifies the direction that produces the steepest, which increases in E. See, that negative of this vector therefore gives the direction of the steepest that decreases. For example, we have already seen in the diagram that arrows shows that negated gradient, which represent in the form of minus delta E of vector of weights for a particular point in the W0 and W1 plane. So since the gradient specifies the direction of steepest increases of E, the training rule for the gradient descent is denoted in this form. So where delta W, that is vector of weights, which is given as a minus n delta of E of vector weights. Here n is the positive constant, which is called as the learning rate, that determines the step size in the gradient descent search. This you have to understand carefully. That is learning rate. The negative sign is present because we want to move our weight vector in the direction that decreases our error value. So this training rule can also be written in its component form, that is in this form. Here you can consider this entire equation as equation number 5. So which makes clear that steepest descent is achieved by altering each component of Wi of weight vector in the proportion of rho E divided by rho Wi. So to construct a practical algorithm for iteratively updating weights according to our equation, we need an efficient way of calculating the gradient at each step. The vector of dou E by dou Wi derivatives that forms the gradient that can be obtained by differentiating E from equation 2. So here the component that we have seen here, that is dou E given dou E by dou Wi, which is given in this form. So by applying your partial derivatives, we get the values here. So substitute the values accordingly. So finally you get the answer in the form of equation. So this entire equation number 6 is substituted in equation number 5, which produces the weight update rule for our gradient descent. This is our equation. So to summarize, the gradient descent algorithm for training a linear unit is, let me explain it clearly. So we have to pick an initial random weights vectors, apply the linear unit to all the training examples. So then you compute delta Wi for each weight according to the equation that what we have received here. So update each weight Wi by adding our delta Wi, then this process is repeated. So this algorithm will be explained in detail in the next slide. So because the error surface contains only a single global minimum, this algorithm will converge to a weight vector with minimum error, regardless of whether the training examples are linearly separable by giving a sufficiently small learning rate. So if learning rate is too large, then the gradient descent search runs the risk of overstepping the minimum in error surface rather than settling into it. For this reason, one common modification to our algorithm is to gradually decrease the value of learning rate, that is n, as the number of gradient descent steps grows. So this gradient descent algorithm for training a linear unit will be explained in a very short form. So here I want to identify what would be the weight vector, this Wi given by Wi plus delta Wi. This is what actually I wanted to identify, that is weight vector. Assume that you are going to identify the weight vector, that is W1, which is given by W0 plus delta W0. So how do you identify this delta W0 and W0? Let's see this one according to this our algorithm. So initially this Wi is initialized to some random values, means this W0 has been initialized with some random values. Next one is until you have some termination condition, you need to perform these many steps. So the step is initially I need to identify this term. How do I do? So initially I use this equation to identify this value. So what I do, initially I set delta Wi is equals to 0. So for each of the input, that is instances, I need to compute the output. So if the output is not as we expected, we are forced to change the weights. So how do we change the linear weights? Again, we have to identify this delta W by using this equation. So this equation, that is how do you got the values here, delta Wi, as initially we have set this delta Wi as 0 here, plus the learning rate times T is our target output minus actual output, that what we have received from our network, times actual instance. So when you apply this entire term, when you compute this entire term, you will receive this updated weight vector. This is similar to this one. So plus this value substituted in this equation, plus W0, as we already know that it has been set to some random values. So this random value plus this weight is substituted here. So delta W0, you will get an updated weight vector. So this is how we calculate the weight vector by using gradient descent. I hope you have understood clearly. Let's see some of the features of a gradient descent algorithm. This gradient descent is an important general paradigm for learning, and it is a strategy for searching through a large or infinite hypothesis space that can be applied whenever the conditions are when the hypothesis space contains only continuously parameterized hypothesis. Example, the weights in a linear units. Second one is the error can be differentiated with respect to the hypothesized parameters. So there are some of the key practical difficulties in applying our gradient descent. One is converging to the local minimum can sometimes be quite slow. That is, it may require many thousands of gradient descent steps. And second one is if there are multiple local minimum in an error surface, then there is no guarantee that the procedure will find the global minimum values. See, one common variation on gradient descent which is intended to elevate these difficulties is called as incremental gradient descent, and sometimes it is called as stochastic gradient descent. See, whereas in the gradient descent training rule, which is presented here in the equation number 7, so that equation, this entire equation computes weight updates after summing of the training examples in D. So the main idea behind the stochastic gradient descent is to approximate this gradient descent search by updating weights incrementally. Remember this one. Whereas in the standard gradient descent, the weights are updated after summing over all the training examples. But whereas in the stochastic gradient descent, the updating the weights will be done incrementally, that is by instance, that is following the calculation of error for each individual examples. You can see this equation here where T, O and Xi are nothing but your target value, unit output, and ith input for the training example in our equation question. Here you can see the stochastic approximation to the gradient descent, and the steps here is same as our standard gradient descent algorithm. Here we do have the two parameters, one is training examples and learning rate, and the training example which is given to this algorithm, it is of a pair in the form of weight vector along with the target output. Here as you see that weight x is the vector of input values, and t is nothing but your target output value, and n is your learning rate, which is kept as small as possible. So the first step is initialize each weight to some random values. So until you meet some termination condition, you have to repeat these steps. The only difference between the standard gradient descent and the stochastic approximation is you can see in the previous algorithm these two equations have been used here. So here for each of the input, that is x and t in the training examples, first thing is you need to compute the output O for a given instance x. Second step is for each of the linear unit weight you need to identify W0. But whereas in the previous algorithm, here you need to identify this delta Wi, where it is given in the form of delta Wi plus learning rate t minus O into x. So this entire term is replaced with this equation for our stochastic, and this second equation has been removed because here we are concentrating only on an individual instance. We are trying to identify the weights for an individual instance. we are going to identify the weights. So one way to view this stochastic gradient descent is to consider an identical or distinct error function E of weights, which is defined for individual training example D as follows. So where TD and OD are nothing but your target value and unit output value for training examples D. This stochastic gradient descent iterates over the training example D in D. At each iteration, altering the weights according to the gradient with respect to this term. So the sequence of these weight updates when iterated over all the training example provides a reasonable approximation to descending the gradient with respect to our original error function, which is given as E of weight vector, by making the value of learning rate sufficiently small. And this stochastic gradient descent can be made to approximate two true gradient descent arbitrarily closely. So we shall see the key difference between gradient descent and stochastic gradient descents. See, the major key differences are noted here. In the standard gradient descent, the error is summed over all the training examples before updating the weights. But whereas in the stochastic gradient descent, weights are updated upon examining each training examples. This is very important that you should understand. See, summing over multiple examples in the standard gradient descent requires more computation per weight update step. See, on the other hand, because it uses the true gradient, standard gradient is often used with a large step size per weight update than stochastic gradient descent. So in cases where there are multiple local minimal with respect to stochastic gradient descent, can sometimes avoid falling in these local minimal because it uses the various error value with respect to an individual instance rather than your set of instance to guide its search. So these are the key difference between the standard gradient and stochastic gradient descent. Let's see some of the remarks that what we have discussed till now. So we have considered two similar algorithms for iteratively learning perceptron weights. One of the major key difference between these algorithms is that the perceptron training update rule weights based on the error in the threshold perceptron outputs, whereas in the delta rule updates weights based on the error in the unthreshold linear combination of inputs. This is one of the major remark. Second one is the difference between these two training rule is reflected in different convergence properties. See, in the perceptron training rule converges after a finite number of iteration to a hypothesis that perfectly classifies the training data. The condition is provided the training examples are linearly separable. But whereas in the delta rule, that will converges only asymptotically towards the minimum error hypothesis, possibly which requiring unbounded time, but converges regardless of whether the training data is a linearly separable or a non-linearly separable data set. So these are the two important remarks that we have identified by within this learning perceptron weights. Now in the next we shall see the multi-layer neural networks and the backpropagation algorithm. This completes the session 4, and in the next session we shall see multi-layer networks and backpropagation algorithm.